this line because, again, remember what we want to do is, for some data, the test really becomes a question of, okay, I find this trend, and I'm really interested in the slope of that trend. So remember, the slope is just the change in y. So change in y over change in x. So we'll get some estimate for the slope, and then the actual test, the p-value we get, is the question of, well, is that slope enough different from 0 that we think it did not happen by chance? Okay, so our H0, our null hypothesis, will be that, now you're used to using an M, they often use a B or beta, and so I'm going to say, B is equal to 0, that's the slope, and the alternative is that B is not equal to 0, and so, H0 is really talking about independence, and HA is talking about dependence. Okay, so how, so it's very important how that slope is made and so forth, and it's probably good to kind of think of the modeling aspect for this. And as I look at this, I could take all the x values and just the x values, and I could compute x bar, the average. Right? So I can compute x bar, and so that's going to be my x1 plus x2 plus to some xn for how many I have divided by n. Or another way to write that is use a summation. That's an uppercase sigma. So that just means add up all these things that you see, and we'll probably say xi, and then divide everything by n. Now, I could go so far as to, in here, say I equals 1 to n to tell you how to add it up. But I think the important part is when you see that sigma, you're really just saying add everything up that looks like that. And so that's x bar. And it would be in the middle of all the data from the low end here, the minimum to the maximum x. And so x bar is in there somewhere. And, here, if I had to predict a y value, so if I had to predict a y value, but just one, right? I just said, okay, I'm going to predict that y is some number always. Well, what would be a good one to predict? And, well, we've been doing this. I mean, if you get a bunch of y values, a good way to predict what the y value is to talk about the average y value. And so we would have that, the sum of the yi's divided by n. And that, again, well, it'd be in the middle from the high and low part, so, it'd be somewhere in there, y bar. And I'm going to go here, and, well, I kind of missed. Okay, there it is. Don't wreck a good story with facts. We'll add some more data to make it look good. Okay. So there is the point, x bar, y bar. And so in the most simplistic way to model or predict the y values, I guess that would be it. I just use the average y value. And then if I wanted an x value to go with it, probably the x bar. Okay, so we start there, and that is a perfectly good model. It doesn't do great because, definitely in this data, it looks like there's some kind of trend going here. So really, if I had a lower x value, I'd probably like to predict a lower y value and a higher x value. decides, okay, I've got that point. I am going to find a line that goes through that point that has the best slope I can find to represent those data. Okay. Now, if you all recall, point slope form and all that stuff, you know, there was this y minus y0. Well, in this case, we know that point was y bar equals, now I'm not using m, I'm using b for the slope, and then x minus x bar. And so, the question is, what's the best value of b to represent these data? And then, the next level of question is, okay, we found that b. It probably won't be exactly 0. The slope won't be exactly 0, almost any data you pick. But the question is, well, is it enough different from 0 in a statistical sense to say that it didn't happen by chance, that it really is, there really is a trend there. In which case, if there is either an upward or downward trend, then, oh yeah, we have dependency. Again, that goes back to the chi-square, the ANOVA, you know, any of those. If there is that difference as we move along the x values, if we would change our prediction of y, well, there appears to be some sort of dependence going on there. And so, the least squares work, and then the least squares results, they are all about looking, well, they do a few other things besides that, but they're all about looking at that slope, and then we want to decide, okay, is that slope enough different from 0 to count as dependence? And so, you know, how do we find that slope? Okay, well, we're going to find it simply by using a spreadsheet and using their code. But it's really not too bad because notice, I mean, we've already got x bar, y bar, and then, you know, to calculate that slope, well, if you're given, you know, you have a bunch of xi's, so you got this, you know, this curly braces, x1, x2, you know, up to some xn, and you're also given a set of y values that go with it, you know, y1, y2, up to yn. Then from that, you could calculate an x bar, you could calculate a y bar, and it turns out that there are various formulas one could use to talk about what that slope is, but b or beta. So if it's a Greek letter, you use beta. B and often we might put a hat on it because it's what we calculated, kind of like we talked about p hat back when we were looking at proportions. But so our approximation for that slope, we can use the formula where we sum up each yi times its corresponding xi minus x bar, like that, divided by the sum of the xi minus x bar squared. And so we can do it that way. There are some equivalent formulas one could use, but again, we're not going to actually use the formulas. We're just going to use software to do it. but that's what it's doing. And what that calculates is if I have, now I'll just use very few data points here. If I have some data points like that, what that, and we find, say, the average is right there, so we get this line. What that line has done is it's taken all these vertical distances like that, and you see if I twist that line, if I spin that line a little bit, those vertical distances will all change. Well, what this b hat does is it finds the slope of a line such that the sum of the squares of all those distances is minimized. And that's why it's called least squares, because we minimized or found the least of the sum of the squares of those deviations. So they're those vertical deviations. Now that's somewhat important to us in that if it, so we've got our x and our y as our explanatory and our response, and the thing is, if I switch those variables, I won't get exactly the same p-value. Now, chances are I'll get a very similar p-value, but not necessarily. Depending on how the data are and so forth, you could probably create a case that's very wildly different between the p-values, but definitely the slopes are opposite, or well, not opposite. The slopes are just different, and but more importantly, from a dependence point of view, the p-values will be slightly different, and so this is the one case really where compared to like chi-squared, where it really does kind of matter what you consider explanatory and response. Now, typically, in the context of any investigation, those do make sense, and probably 99.9% of us would all pick the same explanatory variable, same response variable, or we'd put them in those same lights. But they don't have to be, but it will slightly change answers most likely. But anyway, that's what we're doing with